Okay, this is lecture 13 on invariant maximality derivations by Harvey FriedmaN. Please.
Thank you. Um, so let's just review where we are. Uh, First of all, I should say outright the chapter 4, the reversal, is now on the internet under downloadable manuscripts. Uh, and we have the whole series of lectures on them uh, that are available on Andreas Weiermann's site. So that's done in the downloadable manuscripts. You'll find the one single link for the whole chapter. I erased all those partial links. Now we're going to do the same thing for chapter 4. Excuse me, chapter 3 now. And we start today with chapter 3, first lecture on chapter 3. The book actually there's been some changes. I think, yeah, I've changed the title a little bit of the book, and uh, I'm changing and also the title for the chapters. Yeah. So this is now current. The table of contents is partial for this chapter 3. Introduction will come later. And today we do 3.2 through uh, uh, the first three parts of the first three parts, maybe the first two parts. Sorry, the first two parts of um, of section 3.4. So we do 3.2 through 3.42. The second, the first section we talk about is 3.2. These are the fundamental notions that underpin the entire book of order equivalence and order invariance, underpin the entire invariant maximality. These fundamental equivalence relation, order equivalence on sequences of rationals, finite sequences of rationals, and then also order invariant sets. This is very basic, used all the time. Then we discussed the lead template of invariant maximality, the lead template. So that means there's only one. And the lead template is actually in here. But we first discuss the boldface case. There's a boldface thing, which is not the headline of invariant maximality. But for completeness, we discuss a boldface kind of template. And then we have 7 different, what I call secondary templates, which are more specific to particular interests in mathematics among mathematicians. They're all, they all fall under, they all fall nicely under the lead template, but they're more specific and they are sensitive to particular mathematical interests people have, or mathematical communities, if you like. Squares, roots, Ord squares, emulators, free sets, cliques, independent sets. And first we talk about the boldface part, and then we talk about the part we really care about, which is the lightface part, so to speak. And then we have invariant maximality. So these are now going to be the secondary templates. The seven secondary templates are in here. And actually, we don't quite get to this today. And the next lecture, we'll talk about equivalences and implications. Basically, basically to simplify the claim a little bit, all of these are equivalent, and they seem to be weaker than the Lee template. The Lee template seems to be a stronger template. I think there's some unclear things here, but basically these are all these secondary ones are equivalent. But that's to be discussed next time. All right. Then usability means can you in a template can you uh, use the function and uh, that's what we really care about is usability. In other words, one of these templates true. I'll be more specific in a moment. And then the lecture after next handles the finite case, which is fully understood now. The finite case, what finite functions can you use in the theory? And this doesn't require any set theory. But when we get to infinite usability, things are very different. Then the subject really takes off in terms of its connection with set theory. And then we discussed a number of, I don't want to get too much into this because we're only going to do a little bit today into this. All right. So in other words, there's a lot of material about usability, and some of it is I haven't fixed yet. I haven't completed yet. There seem to be some interesting things that are happening. All right, so let's start with order equivalence. So OE, a nice abbreviation for order equivalence. OE is the equivalence relation on finite sequences of rationals where they have the same length. They have to have the same length, and they're in the same order. So for all I and j, xi less than xj if and only if yi less than yj. Now, it's nice to have a canonical element for every equivalence class. And for various reasons you want to do this. You can think of that as a code for the equivalence class. So let's call a sequence of positive integers compressed if and only if the range is an initial segment of the positive integers. And com of k is the set of compressed sequences. Now, every x in q to the k is order equivalent to unique y in com k. That's an exercise, and that's the essential point. That's a unique collection of representatives. Just saying that the range is an initial segment of the positive integers. All right. So the elements of com k serve as normal forms for the elements of qk. Now, we need a specific one. Well, we just call little com of x the unique, the representative, the unique one. All right. Now, the order type of k, yeah. So maybe I should have defined order type of or OT of k first. Maybe I didn't do that. Yeah, sorry, I have to put that in. OT of k is the number of equivalence classes of OE on Q to the k. It's the number of k tuples, the number of different order types of k tuples. So I'm using OT to mean order type. This is the number of equivalence classes in k dimensions. It's the same as the cardinality of com of k, of course. Okay, yeah. Okay, OT of k is our notation for a famous numerical function. So this turns out this equivalence relation, and the number of elements is well studied going back to Fubini. So this is a very well studied piece of combinatorics. and a couple of references. The Sloan online integer sequence facility, well-known, very useful uh, thing. Uh, all the natural infinite sequences that come up of integers. If you just look at the first few terms, generally that completely determines the rest of it. Not in any formal sense, but in practice, because the number of okay, so it's pretty clear that you could do this. It's a very acute idea, right? You just have to look. So these things are indexed by their first handful of terms, and this is a very important repository that's used by combinatorial people and others a lot. So one of the listings is on Fubini, and that's this OT of K. They're called the Fubini numbers. This is my notation, OT of K. It's not standard. Okay, so these are called the Fubini numbers, the OT of Ks. And there's an interpretation of what this means. It's the number of ways K horses can rank in a horse race, allowing for the possibility of ties. That's how Sloan 64 talks about it. Mendelssohn actually uses horses. Why not? Horse races. Number of ways. In other words, the score sheet on the horse, on the horses, who came in first, who second, third. I mean, including possible ties. There might be 3 horses that came in third or something like that, right? So there's this little paper called Races with Ties that I mentioned, expository paper. But this thing goes back to Fubini. It's kind of old and has a lot of connections with a lot of combinatorial mathematics and even analytic mathematics with power series and so forth. All right, an interval. Yeah, I defined. I don't know why this is sort of uh, screwed up here, but maybe I um, just one second. I want to. All right, let's do this. Let's continue here. Yeah, I should have defined. I thought I have a version which I do. A rational interval is an interval of a rational interval is an interval in the rationals with endpoints from the rationals. Okay, the equivalence classes of OE restricted to J to the K or a natural one corresponds with com K, and there are OT of K such equivalence classes. Yeah. So it doesn't make any difference whether you use all of Q or whether you use an interval. Okay, so you have to prove that. But it has to be a positive length, of course. Now there's a low-hanging fruit. I don't know what happened here. OT of K is less than or equal to uh, what is it? I'll have to look. I'll have to look here just a second. I don't know why this happened. Let me just see for a second here. Okay. Find out just one second. Uh, Hang on. Here we are. Ah, 2 to the k squared. Yeah. Yeah, yeah, yeah. 2 to the k squared. Too lazy to think it through again, so I had to look it up. Okay, so you get an estimate like that. Um, I'm going to follow this by a much better estimate in a second. A preorder on a set X is a reflexive transitive relation. And you can prove that the preorders on 1 through k are in one-to-one correspondence with com k. So counting the number of preorders is really the same as counting the number of equivalence classes here. And there's a published result that says that OT of k is asymptotic to k factorial divided by 2 log 2 to the k plus 1. Now, I guess the combinatorists like to don't want to put parentheses around here. Logicians might. In other words, the 2 comes along with the log 2, which is all raised to the k plus 1. All right. So that's the most well-known asymptotic representation. I don't know how much more detailed work people have done or how interesting it is and all that, but anyways, that's the one that's in this paper. And this paper is 1980s. It's not too old. I mean, by the standards of this subject here, it's not too old. Um, all right. Now here, just to give you an idea of the kind of numbers that come up. So in the Sloan depository, let's call it, are these numbers. OT of 1 is 1, OT of 2 is 3. In other words, the number of order types of a pair. So you can have 1 comma 2 and 2 comma 1 and 1 comma 1. You see how they grow. All right. There we are. I mean, here it gets kind of interesting. OT of 3 is 13 and OT of 4 is 75. Okay. Finally, I define a rational interval properly. I should have done that earlier. Rational interval is extended rational endpoints. So infinite intervals are allowed. And a set is order invariant if and only for all order equivalent of X and Y, X is an S if and only Y is an S. So if you have a rational interval of positive length, the order invariant sets are in one correspondence with the power set of com of k. So the number of order invariant S is 2 to the OT of k. This is my point. The number of order invariant sets in a rational interval of positive length is 2 to the OT of k. All right. X and Y are order equivalent if and only they're the same. Okay, that's a logical issue. So coming back to this table, you can see that the exponent by 2 of these numbers are quite reasonable in this age of computer technology, except here. Here, 2 to the 75 is a pretty nasty number. However, when we do use this, there are plenty of symmetries. So it's not quite 2 to the 75, but it's still pretty hefty. So doing search on the order invariant sets in 4 dimensions for anything interesting is problematic on a computer. You're going to have to use your mathematical brain or whatever mathematical brain AI morphs into in order because 2 to the 75 is a big number. And even if 2 to the 75 divided by 8 or something is still pretty big. All right. Yeah. So if X and Y are order equivalent, then they have the same first order properties in Q less than. This is standard quantifier elimination for dense linear orders has a lot of consequences like this that are very well known. Elimination theory for dense linear ordering is all that's going on here. Now, here's encapsulation. The following are equivalent. S is zero definable over Q less than, meaning first order defined with no parameters. S is defined by a propositional combination of inequalities. S is the union of equivalence classes, and S is order invariant. These are all the same. And also you can replace Q with any non-empty open and rational interval. All right. Now, some of theorem 327 is false if you have a rational interval with endpoints of positive length, because you might have this endpoint, because the constant sequence P is obviously zero definable over Q less than, because you can define P as the least or greatest element. But this is obviously not order invariant. Okay, so you have to be careful with this. It's only for open intervals that you have this. All right, here now. All right, if you have a rational interval of positive length, the following are equivalent. And here you might have endpoints. S is the intersection of a zero definable set in the whole space with J to the K. Okay. And S is defined by a propositional combination of equalities. All right. And S is the union of equivalence classes in OE slash J to the K. And S is order invariant. Yeah. Okay. Now, the order invariant sets for dimensions 1, 2, and 3 are reasonably manageable at 2, 8, and 81, 92. And for K equals 4, as I said, you run into 2 to the 75. This comes up because in our secondary templates for the only dimension 2, K equals 2, they involve order invariant relations on the interval -1, 1 squared, which are order invariant subsets of Q -1, 1 to the 4th power. Although there is much symmetry to exploit it, this is still rather challenging for computer investigations. So you really need to do something, very likely. And of course, if K equals 3, then you're talking about order invariant subsets of Q -1, 1 to the 6th, which is 2 to the OT of 6. And that's, of course, in a totally different realm. All right, since invariant maximality lives in Q -1, 1 rather than Q, we sometimes need to adjust in the technical treatment com K and com K, because they were only with positive integers, if you remember. So you use the minus reciprocal. Minus reciprocal is a pretty good thing to use, because then everything stays in here with coordinate-wise negative reciprocal. So you can use canonical representatives that way. Okay, this means the power set, by the way. Now, there's a more even more robust notion called order theoretic. And this is with parameters. So an order theoretic subset means there are many equivalent definitions. This is all from this elimination of quantifiers with density orders. If and only if there exists Q1 through Qn in the interval, an order invariant T in dimension K plus 1, such that this set is the projection down to K dimensions. So it's a projection down to K dimensions of a K plus N dimensional order invariant set. That's probably, in some ways, the nicest definition. But then, of course, it's equivalent to a bunch of other things. For instance, first order definable with parameters, right? And defined by a propositional combination of inequalities V1 less than Vj, Vi less than Vj, but Vi less than P and P less than Vj, Vi are needed, where P serve as parameters in the interval. Okay, so that's some elementary stuff that needs to be said. Now we get to the lead template. Actually, we start off with some boldface stuff, but we're always going to write -1, 1. We're going to leave the Q off since we know that we're only talking about rationals in this chapter, and in invariant maximality, we only talk about rationals. Section 2, which was about real functions, was an introduction with core mathematical connections, and there it was more natural to talk about real functions. But here we're talking about only rationals now. Rather than just give you all this overview, let's get going with this. All right, so there's a thing called the general constraints. The general constraints. This is the key idea. A general constraint on the subsets of -1, 1k. That's the notion we want. A general constraint on these sets is a condition on these sets of the form S to the R is contained in E, where E is a KR dimensional set given in advance. So you have a KR dimensional set given in advance, and you have the inclusion relation S to the R is contained in E, where S has dimension K, so everything matches in dimension. So when you raise it to the R, you get something that's KR dimensional, right? A solution to this general constraint is merely an S contained in -1, 1 to the K, such that S to the R is contained in E. Now, this is, I think, a rather friendly, clear idea using the language of constraints so that it's quite memorable. The variants that we're going to talk about, remember I talked about 7 variants, will not use the language of constraints and will be more specifically aimed at certain mathematical sensibilities, certain mathematical interests people have. All right. Notice the condition S to the R contained in E asserts that the KR coordinates of every sequence of R elements of S obey a relationship. Membership in E as a sequence of rationals of length KR. Since E is not restricted, we use the name general constraint. Now, we actually are much more interested in a small subset of the general constraints. We don't really care that much about the general constraints, but for the point of view of making this crystal clear what the subject is and means, we discuss general constraints as well. All right, so a maximal solution to a general constraint is a solution which is not a proper subset of any solution. Just the most obvious notion of maximality, where we're just talking about inclusion. So we now consider the following statement, and I write it as GC/max, GC meaning general constraint. Every general constraint on the S contained in -1 to 1 to the K has a maximal solution. And we prove that in RCA naught. It's an inductive construction, a so-called greedy construction, where you try to keep your partial solutions going, where they grow into a total solution. Okay, but there's some meat in that. I mean, it's okay. It can be done in RCA naught. I mean, all kinds of things happen that you can't predict very well. I mean, that's a vague comment, but it'll be clearer as we go on. All right, now the order constraints is what we really care about. So an order constraint is simply a general constraint where the constraining E is order invariant. So a solution to the order constraint is just an S such that S to the R is contained in E. And a maximal solution is the solution which is not a proper subset of any solution. All right. Note that the condition S to the R contained in E asserts that the KR coordinates of every sequence of R elements of S obey a purely order theoretic relationship without parameters. Membership in E is a sequence of rationals of length KR. Hence the name order constraint. There are only finitely many order constraints in dimension K and R. If K and R are fixed, there are only finitely many of these. All right, every order constraint on the S contained in -1, has a maximal solution. That's a special case, right? But the construction is entirely effective now because we're starting with an effective enumeration of the entire space -1, so we can replace RCA naught with EFA, exponential function arithmetic, with the usual understanding that such existential second order statements. If you have an existential second order statement and you want to claim its provable in a system of first order arithmetic, it just means that you have a witness of the existential second order quantifier with a suitably effective defined set that you can prove works. And OC of max is provable in EFA because you can do that in EFA. It's a straightforward construction. Because EFA, by the way, is the kind of the almost minimal arithmetic where coding is not an issue of any kind. EFA, think of EFA that way, is kind of a is rich enough to not worry about coding. All right, okay, so then we have a more refined version. OC/max/x time. Every order constraint has an x time maximal solution, where x time means it's of the form c to the n, where n is the number, n is the length of the input, c is a constant. So 100 to the n is an exponential time. 100 to the n is exponential time. 100 can be any constant. Okay, and then you can prove this in EFA. Now it's a real statement in the language of EFA. I mean, interesting to go more deeply into the computational complexity issues, including a completeness of computational completeness. All right, now we go to our main subject, invariant maximality. We add invariance to GC max because GC max just talks about maximality. Every order invariant constraint has an F invariant maximal solution. Now, you remember what F invariant means. Maybe I should have restated that. Yeah. F invariance means F invariance was all through chapter 2 and all through our discussion of chapter 4 with the reversal. It means that if you have P1 through P, a set is said to be F invariant if for every sequence in K dimensions, if for every P1 through Pk in the domain of F, see, F is a partial function from -1 into -1 whenever it's in the domain, you have the tuple is in S if and only if F of P1 through F of Pk is in S. In other words, you're just applying F coordinate-wise. You're just applying F coordinate-wise. I've said this many times, and I'm sure you're familiar with it. All right, but then you have a triviality. This is a triviality. The only way you can be OC of max F if and only if F is an identity function. Because this is, I'm sorry, I'm talking about G. The only way you can since this is bold-faced, invariance is basically impossible, right? And this is a triviality. What we're really interested in is what we call the lead tape template of invariant maximality. Here it is. OC of X, OC of slash max slash F. This is OC. Every order constraint on S has the F invariant maximal solution. This leads to all the excitement of invariant maximality, this template. And we use very specific Fs and some general classes of Fs and so forth. And that's what the subject is basically about. Now we're quantifying over K and the order constraints, and we now treat this function, this partial function, as a parameter. This is a parameter, namely this partial function. A major goal of invariant maximality is to develop necessary conditions and sufficient conditions on F so that OC of max F holds. This already is surprisingly deep, even for very basic F we used in chapter 2, applied to real functions, here adapted to the rationals. Actually restricted. Since we are now in a purely order theoretic setting, we will focus on the choice of F as these functions. Yeah, I think I explained these notions in previous lectures. These are particular functions. This is the function that's the identity on the interval and maps each point, each one of these reciprocals, excuse me, each one of these fractions into the next one. And then these are fragments of this function. These are all restrictions of this function to somewhat smaller domains. Here we don't even use the interval. And then we want to talk about the usability of these. To make a long story short, the usability of this one is reversed to con SRP. This requires large cardinals to handle this one. This one doesn't. These two, Zermelo is enough, and this is Z3 is enough, and here you can do it in EFA and even. Okay, I'm getting ahead of this. So we're really talking about these 6 statements, right? OC max of this function, 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 OC max of this function. This one leading to the large cardinal, necessary, sufficient to use the large cardinal consistency of large cardinals, yes. We universally quantify over both K and N in these statements here. We will quantify over K and N unless we specify otherwise. But sometimes we don't universally quantify over K. Sometimes at the end of this chapter we talk about what happens when you make K equals N. So you just use one variable. Turns out to not make much difference. By the way, that's an interesting point. All right. This one here is the strongest of these that I was talking about. This one here is the so-called lead statement. It's no longer a template because we actually specified the function. This is the lead statement of invariant maximality. We proved this lead statement in SRP plus, which is the natural extension of SRP to make it finally axiomatized. And WKL naught plus con SRP in section 389. Yeah, these are much later sections. In chapter 4, which we just finished, the reversal, we actually proved that this statement implies con SRP. Thus, we get this, that the lead statement is equivalent to con SRP over WKL naught. All right, in section 3.8, this is again way ahead of us. All right. Let's not worry about this. Okay, so now here are the 7 secondary templates sensitive to various mathematical interests. We identify 4 special kinds of general constraints that are particularly familiar to mathematicians. And let's there's one of them that's particularly nice for various reasons that I was able to explain to gifted high school students. Of course, only in dimension two and blah blah blah, a very basic part. But and you'll find that in my manuscript number 117 and on downloadable manuscripts. That's the emulator version. So let's go on, talk about this here. Okay, so first of all, we have five general constraints, five general categories of constraints that are special cases of general constraints. Okay, not quite. There's a footnote to what I said. Okay, a square is an S squared. A maximal square is a square which is not a proper subset of any square. A root is an S, so the S squared is contained in E. Think of E as a binary relation on -1, 1 to the K. A maximal root is a root which is not a proper subset of any root. Using squares, probably the most mathematically direct templates of all for, mathematically experienced person. Just talk about maximal squares and statements. Roots are akin to square roots or sides of squares in basic high school algebra and geometry. They're also pretty basic. All right. Now, S is said to be E free if and only if S squared is contained in E, and for no distinct X and Y is X or Y. And maximal free set means it's free and not a proper subset of any free. Now, this notion of free is akin to freeness in algebra. Maximal freeness, of course, everywhere. And now we have the graph theoretic form. An irreflexive symmetric relation is what I call a graph. It's like a simple graph. It's done with relations. It's more helpful with what I do than than the graph theorists often talk about vertex sets, but unordered pairs, stuff like that. But this is unordered pairs and singletons, but this is better for what we want, our setting. And a graph is just an irreflexive symmetric relation. A clique is the usual definition. S is a clique in E if and only if S squared is contained in E, and that is not right if and only if for all distinct X and Y in A, X, Y, Z. All right. S is a maximal clique if and only if it's a clique and not a proper subset of any clique. S is independent. This time you can write it nicely like this. S squared contained in E is empty. S is a maximal independent set if S is independent, and E is not a proper subset of any independent set. Such an E is called a simple graph. And this is the vertex set. Okay, and this is the adjacency relation. Cliques and independent sets are completely fundamentally graph theory. Maximal cliques and maximal independent sets are everywhere. The order invariant closure of a set is the least set containing it, which is order invariant. There's always an order invariant closure, a good idea. Roots in E, free sets in E, cliques in E, assuming E is a graph, independent sets in E are examples of general constraints. They're all examples of general constraints. Maximal squares are not examples of general constraints because they're not closed downward. A subset of a square may not be a square. However, we do have this. requires some proof. The maximal squares are the same as the maximal solutions of some general constraint. Even if the squares aren't the solutions of some general constraint, the maximal squares are the maximal solutions of some general constraint. So we then have these statements for the five variants, secondary statements, and this is the master one, the just for general constraints, and this one will imply all these others. That's clear. But they're all provable in RCA naught, so there's no issue here about incompleteness. Now, this is a comment about grammatical construction. I decided to use the constraint terminology for this master one, and the others are specific: square roots, free, clique, independent, and then the word max comes in front. That I just sort of explained why I did it that way. Now it's provable in RCA naught that you have all of these: square root, emulator, free, clique, independent. All six of these: 1, 2, 3, 4, 5, 6. This one is you have to use. It's not directly a constraint, but maximal ones are maximal constraints. Okay, and so all of these are provable, and all you have to do is really prove this one, because all the other ones follow. Now, there's 7 ones that we want to consider with order. So there's a couple of different ones here. And instead of using general constraints, we now use order constraints, but with 2 natural additions. Well, first of all, we do the, before we actually do that, before we get into invariance, we talk about exponential time. Remember, we talked about exponential time before. For this one, we proved that this was in exponential time. But all the other ones you can do, all the other ones you can do also in exponential time, following the reason that these are cases, these follow from OC, the boldface follow, the lightface follow and the computational form will follow by similar arguments. Okay, so now, but I did add 2 new ones. Now, notice that these 2 new ones have an interesting feature. The hypothesis is not a set, but a finite set. It's not a ordered invariant set, an infinite set, but the hypothesis is finite. And this is the one that's most attractive. This is the one that's most attractive to high school, gifted high school. I found that this one. Of course, I only pushed them on. We only really talked about k equals 2. And we actually only talked about sets of cardinality 3 or less. And so you get something that you can actually handle by hand. Not clear how you can handle it by hand. You're going to have some big, tired hands if k equals 4. If k equals 3, for example. But I only talk about k equals 2 for them. K equals 1 and 2, yeah. All right. So I use Fin for these. And here's what the emulators are. Emulators are actually rather beautiful. Very proud of my emulators. S is an emulator for a finite set if and only if every pair from it is order equivalent to some pair from the finite set. It's amazing that you can use this to get a large cardinal so easily, this idea. But that's what we're going to see. All right, so, or need a large cardinal to deal with it. All right, so S is an Ord square. This is the same idea, except you start with a finite set of pairs of k-tuples. if only if S is some pair T squared, is some square T squared where every S in S is order equivalent to some Y. Every element of S is order equivalent to some element of E. Okay, these two. Now this one turns out to be more delicate, believe it or not, than this one for various reasons. All right, maxima is defined as usual. And the roots in order invariance, the free sets in order invariance, the cliques in order invariant graphs, the independent sets are examples of order constraints. And then with the maximal squares you need, the maximal ones match, as I said, when you want to do maximal squares. All right. So then we actually have all of this in exponential time here. All right. Now, next lecture, we're going to talk about adding invariance. We don't follow this computational complexity direction. We go to invariance. By the way, there's a theorem ultimately that once you impose invariance, you can't have effectivity even. You ruin an exponential time. That's a more advanced matter we will see much later. And that's not surprising because if I'm going to get to require set theory to prove stuff, it's unlikely that it's likely to be these infinite objects are likely to be non-recursive. All right. So, however, I do want to emphasize that we do have a chapter in this book on explicitly finite incompleteness, invariant finite choice. That's a whole nother story, and that's chapter 5. We're not there yet. All right, I think that I am done. Andreas?